This says prerequisite understanding, things that I'm sort of assuming you already know. Although you've never written logarithm laws with natural logarithm before, they're exactly the same. If you learned in Math 12 that log of A plus log of B is equal to the logarithm of their product, AB, these are all related to exponent laws, right? 10 to the A times 10 to the B is equal to 10 to the A plus B. Okay? Adding exponents is like multiplying numbers here. Multiplying numbers is like adding logarithms, right? The logarithms are the exponents. So all of those things you could write the same way with ln A plus ln of B. It's the other one you have in your calculator. It means natural logarithm from that pre-calculus unit you'd like to drop. Natural logarithm, it's on your calculator, it's that other button, it's just base E instead of base 10. E is that 2.7181, whatever it is. E is the base you get if you continuously compound something, basically. Okay, we looked at that previously. If you continuously and more often compound something, you can use base E to represent that. Things, natural, real-world things, population growth, bacteria growth, radioactive decay, things grow or decay continuously. Your money doesn't grow continuously. You put some money in the bank. The graph looks like this, and then instantly they pay you the interest, and it's like that, right? Whereas when you model population growth, the people are joining the population all the time, and it goes up continuously. So the best model would be using base E, not the way we do it in Math 12. Both of them are good models, but that's what base E is useful for. If you take more math courses, you'll use base E all the time. You won't use base 7. You know how in Math 12 it says log base 7 of 23? You're never going to do that. There's no reason to use 7, right? There's a reason to use base E, 10, maybe 2 or 8 or something like that if it's a computer thing. But who knows? Okay, that's why there's only those two on there. And any other base you can change to what you want using the change of base rule anyways. So I think I will give you a bit of time here to try and see how many of those rules you can generate for yourself. We will pause. Task number one is that. Okay? Task number one is task number one. Task number 2 is this, graphing this thing for yourself. You will discover something for yourself, I assume, once you do the second thing on that page. What is all this writing? Well, I'm just getting smart in my old age, and I opened a page from last year's just so you could check this. Hey, guys, you want to check this, please? This is all stuff you did in Math 12. You have the power rule here. Ln of A to the n, it's the same as log of A to the n is n times log A. It works with natural logarithms too, right? Log of AB is log A plus log B. So it works the same way here. Works the same way with the division, dividing numbers. Ln of e to the x is x. Those operations cancel each other out. E to the ln x is x. Those operations cancel each other out, just like what you did before. Ln of 1 is 0, right? You're saying what exponent does e need to get 1? It needs a 0. Ln of e to the 1, okay, what power of e is it? It's 1. Writing ln of x equals y, you can kind of use the anti-logarithm, base e, to cancel that out and change it to exponential form here. Okay? And then the change of base rule at the bottom here. Log base b of a is log a over log b. It's also ln a over ln b. You can try it on your calculator and check if you want. It would work. That should give you the same thing either way there. Okay? Now, this I want you to do just so you can kind of discover what the derivative of e to the x is. You'll recognize it when you see it. If you graph... This is a way of kind of, if you don't know what the derivative of something is, but you still want to graph, you can get the calculator to do it with that numerical derivative thing. if you put in y1 is what you want, which is, whoops, e to the x, sorry, e power of x. Okay, e to the power of x. We want to know what the derivative of that is. So what we could do is do that numerical derivative thing. Numerical derivative of what's in y1, except not there, variables. It's, y, function 1. You want the derivative of, numerical derivative, remember, it just calculates the number at each point. Vars for variables. You have to tell it what the variable is for the expression. The variable is x. I know that seems like it should be obvious, but you have to put the variable in. Now, normally when you use this numerical derivative thing, you would say, I want the value calculated at 3 or something like that. But we put an x in so that it'll graph it as a function, right? Just the same as any other function. If you wanted to know what e to the power of 7 was, you'd put e to the power of 7. Can we? I'm shouting over your voices again. Can you guys be quiet, please? Okay? Lots of time to talk while you're working, but not right now. Just the same way you put a number in. If you want to know e to the power of 3, you put 3 in there. But if you want the graph, you put x, so it'll graph all the values. Here, normally you'd put like a 3 there if you want the derivative calculated at that value. But we want it to graph the value of the derivative everywhere, so you put in x. You put another x. The first x is just because that's the way that feature works. You have to tell it that the variable is x. Here you have to tell it x because we want all the values just the same way you put an x in there. If I don't know if I gave you a window there, but I think if you were to do the standard one, or actually if you do if you do this decimal one here, that's probably good enough. Okay, so it's going to graph, that's e to the x, and then you're waiting for it to graph the other thing. Something's wrong here, eh? Still thinking. Still thinking. You need, well, let's change the window first of all because half of it's a useless window, right? Hang on. Let's change this window so that we can, so we do this, right?
Same line. Yeah. No, you changed it to a ball.
I've already tried zooming out.
You change it to a ball? You guys are thinking, I was going to change it to a thick line, but, okay? So the first one's going to be a thin line.
Are they the exact same?
Oh, is that one?
They are the exact same. Okay, so this one's going to trace over top of it.
What do you notice?
That one takes so long. That's a good question because it's a way more complicated computation, or however it's programmed to calculate this thing as this. This it can do really quick, right? But this it zeroes in on each particular one, right?
So the derivative of that?
The derivative of e to the x is e to the x. It's its own derivative.
The second derivative is
E to the x. What's the thousandth derivative?
E to the x.
E to the x.
Give me some time. I'm gonna figure it
You want a question like that on the test?
out. Yeah. Maybe like.
This one is e to the u, but times u prime. This is just a chain rule. This is the only new piece of information. I really am not sure why I put this in, because it just makes it seem more complicated. This is just the chain rule here. All right?
The chain rule, everyone.
Pretty much, this is, if you look at, now, if we go to back to the calculator, you want to see that a different way, just calculate the slope of that graph. So get rid of the second part. Right? If you want to see it a different way here, clear that out. Graph this thing and then calculate the tangent. Like get it to draw a tangent somewhere and see how it compares. All right? So it's going to draw this graph. We're going to run out of time, but no, we'll be okay. If you want, you can trace and calculate the, let's do it at 1 here. No, it's 2. Let's do it at, well, I mean, it doesn't even matter, right? Just remember, let's pick a value and remember the y value, okay? So let's do at 0.5. At 0.5, it's 1.648, whatever, right? That's the y value. If you draw the tangent, okay, remember the tangent, what x value did I pick? 0.5. Okay, so remember the y value is 1.64. It's going to draw the tangent, and the slope of the tangent is 1.64, okay?
That's a connection.
You try that anywhere and you see. That's a connection. That's good.